The permutohedron piece of N is an n-1 dimensional polytope Rn, whose vertices correspond to permutations of the vector 1, 2, dot, 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 n, and whose edges correspond to transitions between two coordinates. So, for example, let's go through piece of 2. So piece of 2, you take the vector 1, 2, and you do a basic transposition to 2, 1. And so you take this edge right here, everything in between, that's piece of 2. Piece of 3, you start with the vector 1, 2, 3. You do transpositions all the way around. So you get all the permutations of 1, 2, 3. And you take the convex whole of all those vertices. So this is going to be this hexagon right here. And piece of 4 is going to be this shape right here. Piece of 4 is right there. So that is the permutohedron. Okay, the associahedron, case of n+1, is an n-1 dimensional polytope Rn, whose vertices correspond to a way of correctly inserting open and closed parentheses in a word of n+1 letters, and whose edges correspond to applying the associative rule. So let me show you how that works. So here you start with the letters A, B, C, and you apply the associative rule here. So you get this edge right here. Okay. That's case of 3. So case of 4 is this pentagon, right? We start with A, B, C, D, right? This is a way of inserting parentheses into a string of 4 letters, and then we just apply the associative rule, right? We just go around and apply the associative rule, and we get this tight pentagon. And this is the shape. This is case of 5. That's the associahedron on when you do it with 5 letters. Okay. Now, amazingly enough, there's actually a relationship between these two polytopes, right? So from P2 to P3, they're both edges, right? But from P3 to K4, we start with the hexagon, and we just collapse this red edge to get to the pentagon. And then from piece of 4 to K5, you take the outer shape, the permutohedron, and if you collapse these red edges that I've drawn right here, all those red edges right there, you get that black shape that I drew right there, the associahedron, case 5. So that's kind of interesting, right? I mean, remember I told you that the permutohedron was made by permuting those coordinates, right? By basic transpositions. But the associahedron is defined completely differently. It's defined by applying the associative rule to a string of n letters. So that's really interesting that there's a relationship between these two. So the collapsing map from piece of n to case of n+1 can get very, very complicated in higher dimensions. So here's a piece of P6, right? We've got like 11 vertices here, 3 faces, a whole bunch of stuff. They all collapse to a single vertex on the associahedron. So I want to count the number of K cells on the permutohedron piece of n, which collapse to a vertex on case of n+1. So a K cell is just a generalization of vertices, edges, faces, where vertices are 0 cells, edges are 1 cells, and faces are 2 cells. So for instance, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 0 cells on the permutohedron P6 is collapsed to the single vertex or 0 cell in K7. So that's what I'm going to ask and figure out. Okay, so in order to describe this collapsing map, though, from the permutohedron to the associahedron, I need to introduce these things called P-trees. So P-tree is just, all it is that every leaf of the P-tree has the same height, right? The same height from the root, 1, 2, 3, 4, 5, 6, 7, 8. And also at every level, something's happening, right? So there's there exists at least a node that has more than 1 child. So for example, this is not a P-tree because if you look at this level right here, they all go down. They only have 1 child. This guy only has 1 child, 1 child, 1 child. Whereas this one is a P-tree because if we look at every level, we can find an internal node that has more than 1 child. Like this one right here, that one right there, that one right there, that one right there, that one right there, there. So that's what a P-tree is. So we can label a P-tree based on the heights of the gaps. So for example, this P-tree right here is labeled 2517463 because the first gap has height 2, 1, 2. The second gap is height 5, 1, 2, 3, 4, 5. the third gap has height 1, the fourth gap has height 7, and so on. You notice that I wrote it in a specific way. I wrote it like a vector, right? That should give you an idea of what I'm trying to, like this guy right here is actually going to be attached to a vertex, the permutohedron, 2517463. So we can actually, using this label system, we can show that the K cells in the piece of N, the vertices, the edges, the faces, they correspond to P trees with N+1 leaves and height N minus K. So I'm going to show you how it works for piece of 3. This is what you do. You take, this is how it works right here. So you can see, like for example, this tree right here, what's this? This is 1 or 2, 1, 3, right? This is vector 2, 1, 3 associated to him. And this edge right here corresponds to this tree, P tree right here, and this face corresponds to that P tree. Okay. So that's how you assign each P tree on 4 leaves to piece of 3, the permutohedron piece of 3. Okay, now I'm going to tell you what a K tree is. A K tree is an ordered tree such that every internal node has at least 2 children. So we can express the associative rule using K trees, right? So this is the associative rule right here. This is a K tree. Every internal node has at least 2 children. And so that's that. More generally, a correct way of inserting parentheses into N+1 variables can be used by using binary K trees. So, and we can furthermore show that the K cells in the case of N+1 correspond to K trees with N+1 leaves and N minus K internal nodes. So I'm going to show you how it works for case of 4. So this is what you do. This is how you attach each K tree on 4 leaves to each cell of the case of 4. Okay, so now I'm going to describe to you how this collapsing map works in terms of these trees. So given a P tree, we can obtain a K tree T bar by deleting the internal nodes, and we call this the collapsing map. So for example, right here, this guy right here goes to this guy right here. So all the internal nodes, we just delete them, get rid of them, right? And that's what we get right there. So this collapsing map from the collapsing map from the permutohedron piece of N to case of N+1 corresponds precisely to this collapsing map in terms of trees, right? So if I want to count the number of K cells in piece of N which collapse to a vertex in case of N+1, I have to do the equivalent count of the number of P trees with N+1 leaves with height N minus K, which collapse to a specified rooted binary tree. And so this is the formula that we get, where piece of KT is the number of K cells of the permutohedron. And you can see it's a recursive formula. So it's determined by the I cells and J cells that are smaller than K. So it's kind of a very interesting recursive formula. Okay. I just wanted to make another mention that what this collapsing map right here, there's something very interestingly algebraic going on, right? I mean, there's something very algebraic about it. So what is it? So you take this tree right here, for example, and AB, you apply AB, right? You multiply them together. But while you do that, everything else, you apply a function f, right? F of C, F of D. That's what the internal nodes with one child correspond to. So if you do this, you get these guys right here. This collapsing map right here can be represented by just setting f equal 1, the identity function, right? That's how we normally add things. So I'm going to show you an example where f is going to be multiplied by x, right? So what do? So we start with 1s on the bottom, right? Add them up, add them up. But when we get to an internal node with only one child, we just multiply it by x, right? Add them up, 2x, 2, 2. Do the same thing here. And we get 8 plus x. There's a whole bunch of interesting things that go on right here. For example, the polynomial that you actually get, you can actually see that the coefficient 8, the reason why that comes up is because there are 8 paths from the leaves to the node. 8 paths that do not cross an internal node with one child, right? So this is the internal node with one child. So there are 8 of them that go through from a leaf to root that do not pass a node.